A sequence is a list of things. We sometimes say that it's an ordered list to emphasize that the order matters. Sequences can be finite or infinite. Infinite sequences are usually indexed by the natural numbers 0, 1, 2, 3, and so on. We can denote an infinite sequence in many ways. Some common ones include this notation with angled brackets. The a followed by the subscript n is read as a sub n, and the vertical line is read as such that. So we read this notation as the sequence a sub n such that n equals 0, 1, 2, etc. Sometimes parentheses or curly braces are used in place of angled brackets. All of the sequences we're going to deal with in this video are infinite, and when that's understood, we often write just the a sub n part, omitting the range of the index n. It's worth noting that these two examples, while sometimes used, are dangerous, since curly braces are most commonly used to denote sets of objects, and sets don't have any order. It's therefore best not to use this notation, but it's good to be aware that some people might. Our main concern at the moment is with the limits of sequences. Before we define that, let's review the definition of the limit of a function at infinity. To say that the limit of a function f of x as x approaches infinity is a means that for every epsilon greater than 0, there's an m such that the absolute value of f of x minus a is less than epsilon whenever x is greater than m. To see what's happening with this definition, let's look at this graph of a function. To say that the limit is a means that no matter how narrow a band we put around a, there's a point on the x-axis beyond which the function's graph is entirely within the band from that point on. With this in mind, we define the limit of a sequence a sub n to be a number a such that for all epsilon greater than 0, there's a natural number n such that the absolute value of a sub n minus a is less than epsilon whenever n is greater than or equal to capital N. The notation that we use to denote the limit of a sequence is similar to the notation we use for a function. By convention, the letter n ranges through whole numbers, so this is different from writing x going to infinity. There are also definitions of limits of sequences equaling positive or negative infinity. Both of these are also analogous to the definitions of limits of functions equaling infinity. These limits don't exist in the strict sense, but in some contexts, such as the conditions required by a particular theorem, they're grouped with limits that exist. Many of the tools available to us in the case of a limit of a function are also usable in the case of a limit of a sequence. For example, suppose that a sub n equals 1 over n. Then the form of the limit as n goes to infinity of a sub n is 1 over infinity, which is enough to tell us that the limit equals 0. Another example is this one, in which a sub n is a ratio of polynomials in n. We can evaluate this limit by dividing the numerator and the denominator by n to the fourth, from which we conclude that the limit is negative 3/5. We can also benefit from tools that require functions. To start, let's note that if there's a function f of x such that f of n equals a sub n, and the limit as x goes to infinity of f of x is a, then the limit of the sequence is also a. To see this, let's go back to this graph. Here's the limit a. Remember that no matter how narrow a band we put around a, the function's graph is always within the band after some point. Since the terms of the sequence are all given by values of the function, we can represent them as points on the graph, which means that they must all eventually land within the band after some point. To see the benefit of this, let's look at one more example. Suppose that a sub n equals 3 to the n over 5n. Then the limit of the sequence is the limit of this function as x goes to infinity. To evaluate this limit, we can apply L'Hopital's rule, which turns the expression into 3 to the x times natural log of 3 over 5, whose limit is infinity. Let's end with a question that asks, in essence, whether we can reverse this process. If f of x is a function satisfying f of n equals a sub n for all n, and the limit as n goes to infinity of a sub n equals a, then must the limit as x goes to infinity of f of x also equal a?